Hello again. We have defined the reliability for a system. Now we want to define the hazard and hazard rate. Hazard rate is stemmed from the conditional density. So the conditional density fx of x is a function of x and t. Obviously, x shall be bigger than t. The hazard rate is just defined if you replace both x and t by t, we define it as hazard rate. So is that the first argument, which is not t, if you both put. So hazard rate means just the value of the PDF around t, that in the vicinity of t, what is the density of having a failure, or is called rate of hazard. So because this guy was fx of x divided by r of rx of t, so if you replace this by t, you get this one, and this is complementary PDF. So hazard rate is just the ratio of the PDF divided by the complementary PDF. You can also see that if you calculate d to dt of ln of rx of t, this is equal to this one, because this is equal to derivative of or is equal to minus this one, because rx of t is 1 minus fx of t. Okay, so derivative of logarithm is equal to, this goes to the denominator, and derivative of 1 minus fx of t, so which is going to give you the PDF. So the hazard rate is that you plot the reliability. Reliability itself is a decreasing function, rx of t. If you plot it in a log scale, okay, minus ln of that, so at this point r of t is 1, so its ln is 0, okay, and because this function is decreasing, the ln should be decreasing, but because we have a minus here, so this is going to go up. So this is minus ln of rx of t. So the hazard rate is the slope of the reliability. So it says that, so if hazard rate at a certain point in time is large, so the rate of incidence around that point is going to be very big. But if it stays constant, that means that it's... So the value of beta dt, if you multiply it by dt, is the probability that a system functioning at time t will fail in the interval of t plus dt. This is provided that dt is very small enough. So this is an approximation. So this approximation is exact if dt is very small, but it's a good approximation if dt is small enough. So from this expression, you can see that this is equal to minus derivative of rx of t divided by x, which is minus derivative of the ln. As example of hazard rate for exponential PDF and the CDF 1 minus e to the power minus ct ut, because if you integrate it, you get this one. You will get quickly the hazard rate as follows. So so here you get minus c e to the power minus ct, and then here you get e to the power minus ct, and then it will become minus c. It will become equal to c. So so quickly you see that exponential distribution, the hazard rate is constant, and this is the only distribution which has a constant hazard rate. That means that as time goes by, as long as you don't have a failure prior to the current time, the distribution, the shape of distribution is unchanged, and therefore the hazard rate is not changed either. So this system has a constant hazard rate, the hazard rate is calculated from, in this expression you see that Rx of t is equal to 1 minus fx of t. So using the distribution you can calculate the hazard rate. But we'll see that the distribution also can be calculated using the hazard rate. Always the hazard rate is not negative, is positive. The hazard rate is defined by this expression. Now we wonder if we can calculate the distribution PDF or CDF provided that the hazard rate is given to you. So we can inversely calculate this one using the hazard rate. So we use the same equations we have, and obviously this guy is the derivative of ln of Rx of t. So if this guy is given, I could say that minus ln of Rx of t is equal to integral of beta x of let's say x dx, and x varies from 0 to time t. Okay, and now I could multiply both sides by a minus sign, and I say e to the power of both sides. E to the power of ln becomes this function, so you get exp of this function. So I have this formula using which I could calculate the reliability, which is equal to 1 minus fx of t. So therefore from here I could calculate the CDF, and then from there I can calculate the PDF. So so from here you can have this one quickly and then see that Rx of t is equal to e to the power of integral of the there is a typo here. This should be t, this should be x, because here the dummy variable is over x. So from here, if I calculate minus derivative of these, I get this expression. So it's minus d to dt, and then replace t by x. Obviously I get the PDF. So this is a general formula that you can calculate the PDF using the hazard rate. So so a system is called memoryless if its hazard rate is constant. So this is another definition for a memoryless system. That is the probability that it fails in an interval of tx, assuming that it is functioning at time t, depends only on the length of this interval. So this is another definition for a memoryless system. So a memoryless system has an exponential PDF. So if you summarize this definition, is you say that probability that x fails in the interval of t and x, provided that it's functioning at time t, is a function of the time difference. So you say that this is a memoryless. Now, using this definition, you can prove that f(x) of x must be equal to c e to the power minus c x ux. There is no other way. This is for the case of continuous type random, but if you have discrete type, this shall be, you can prove it, this shall be a geometric distribution.